Hello, everybody. How are we doing today? Hopefully, we are all doing well. Today, our plan is to go over our notes on periodicity or periodic trends. So for that, what you're going to need is you're going to need obviously something to take your notes on, so something to write with and a piece of paper or the notes that you got off Canvas. And then you'll also need a periodic table, which again, you can find on Canvas. All right, so we're going to go ahead and get started. So let's do that. All right, so here I have notes on periodicity. So our periodic trends, they're basically patterns that we have found on our periodic table that can help us predict what those elements' properties are going to be. And so that's the entire purpose of these periodic trends, is to help us predict and try to figure out what's going to happen as we continue across or down or up or whatever on our periodic table. Okay, so here's some things to remember. First off, while you're in the gas phase, remember your definition. Okay, this is for your AP test. Remember your definition should include ionization energy and electron affinity. Okay, so and we'll get to those in a second, but you should include ionization energy and electron affinity in your explanation. Okay. Second, remember that a trend is not really an explanation. It's an observation. So it's never okay to say, okay, I'm moving from left to right across the periodic table, so that's why this is happening. You have to use the trend specifically where we're talking about, you have to use the trend specifically where your explanation is going to be your justification that'll give you for each individual one. Okay, so like moving from left to right, you could say something like an increase in your effective nuclear charge, but you can't say that's changing because I'm moving from left to right across the periodic table. So you shouldn't be talking about the direction you're moving when you're justifying what's going on. Okay, all right, so let's go ahead and dive on into this. So atomic radii. So this is really the size of an atom that we're talking about. Okay, so as I move across my periodic table or down my periodic table, my size is obviously going to change because I'm changing my number of protons and electrons and neutrons and energy levels and all those kind of things. So let's talk about why that actually occurs. For your atomic radii, as you move down a family or down a column, your size is going to get larger. Okay, and the justification that you should use when you're on your AP test is that as you add energy levels to an atom, the distance from the nucleus to the outer edge increases. Okay, well, that kind of makes sense, right? So if I started off and I'm hydrogen, I've got the nucleus, which has got the proton in it, and then I've got an electron that is orbiting that nucleus, and the distance from that proton to that electron at any given time, it's going to be pretty consistent. It's going to be really, really close, right? Whereas if I move down an energy level, for example, if I move to lithium, okay, we got some protons and we got some neutrons. Okay, so I've got 1, 2 on that first energy level, and then I've got one more that's on that next energy level. So this distance here has increased in comparison to that hydrogen. Okay, and we can use a Bohr model. But again, the Bohr model we obviously know is not the correct way to really show what's going on, but it is a good way to get a general idea of what's going on. Okay. Okay. So again, as you move down a family or down a column, you're going to be adding an energy level, which means it's going to be larger. Okay. So you're increasing the distance from your nucleus to the outermost electrons. All right. Now, as I move from left to right across the periodic table, we're going to decrease in size. Okay, well, that's kind of strange, right? You're adding protons, you're adding electrons. Well, you're like, okay, well, I'm adding more stuff, so it should be bigger. But when we add more protons, we're going to have more what's called ZEF, or effective nuclear charge. And because we've got more ZEF, it's going to have a stronger pull on those electrons, and it's going to pull them in closer. All right, it's going to pull them in closer. I kind of like to think of this like a rubber band. If I've got one rubber band holding on to, let's say I put one rubber band between my fingers. If I've got one rubber band, it's going to be easy for me to hold my fingers apart. If I add two, it's going to get a little harder. If I add three, a little harder. And as you add more and more and more of those, it's going to get harder and harder and harder to hold those apart. So my fingers are going to get closer and closer and closer and closer together. Okay? So the justification for as you move across your periodic table is it is increasing the effective nuclear charge, which means it's increasing that attraction from those protons to those electrons, and it's going to pull that electron cloud a little bit closer in. Okay? So your size gets smaller as you move from left to right across the periodic table because you increase your effective nuclear charge, which increases the attraction, which pulls those electrons closer together. Okay? So for this, you do need a periodic table. Okay, so hopefully you've gotten a periodic table. Go ahead and pause if you haven't, but let's go ahead and solve this problem. So it says, which of the following has a larger atomic radii? So I've got zinc and titanium. Well, if you look on your periodic table, zinc is number 30, and titanium is number 22. Okay, so I'm trying to compare those and trying to see which one has the larger radii. Okay, well, we're on the same energy level. Okay, so if we're on the same energy level, we know that we can just use our number of protons to help us decide which one's going to be smaller and which one's going to be bigger. Okay, so zinc has 30 protons, titanium has 22. Okay, so we're staying in that same period, that same row on the periodic table. So I know that as I move across my periodic table, I'm going to be increasing my protons, which increases my Zeph, or effective nuclear charge, which increases that attraction, which is going to then increase or decrease that distance from the protons to the electrons. So those electrons are going to be pulled in a little bit closer. Okay, so since zinc has more protons, it's going to be smaller. Okay, since titanium has fewer protons, again, this is only in the same period, the same row. Since titanium has fewer protons, it is going to be the larger atom. Okay? Next, which of the following has the larger atomic radius? Again. Okay. Now, what we're going to do is we're actually going to look at these and see where they are on the periodic table again. So I've got silicon, and silicon is atomic number 14. And then I've got indium, which is atomic number 49. Okay, and I'm going to compare them. Now, these two are not in the same row or period. So since they're not in the same period, we're going to have to look at our distance from the nucleus, so our number of energy levels instead. Okay, so I've got indium, it's number 49. Indium is actually 2 rows below. Okay, so it's got 2 additional energy levels. Okay, silicon is on energy level 3. Indium is on energy level 5. Okay, so what I'm going to do is I'm going to actually look at these and I'm trying to figure out which one's going to be larger. Okay, well, again, as I move down my periodic table and I get more energy levels, let's look back at our justification. So as you add energy levels to an atom, the distance from the nucleus to the outer edge increases. Okay, well, since indium has more energy levels, the distance from the nucleus to the outermost electrons is going to be much further than silicon. So indium is going to have a larger atomic radii. Okay, and this is kind of what you see here in this picture. Okay, it's kind of giving a general overview of what it would look like, and it's all in comparison to the other things in that period. Okay, all right. So now let's talk about ionic radius. So this happens when an atom either gains or loses an electron. Remember, that's how we make ions. We got cations and anions. So when this happens, we're changing that proton to electron ratio, right? So when we change that ratio, we're going to change how close those electrons can be together. Okay, so here we go. Here's your justifications that you would use on the AP test. If you've got a cation, cations are smaller than their neutral atom because when we lose an electron, usually that's going to eliminate that principal energy level, that valence energy level, that valence shell. And because it reduces that valence shell, it's going to make that smaller. Okay? Now, if it doesn't completely get rid of that energy level, that's okay, but you still have the argument that the nucleus is attracting fewer electrons, and thus it can pull them closer. So you can kind of think of this like Zeph in a way, where we're talking about, okay, well, I've got more protons than electrons, so those protons can pull harder on the electrons, which is going to pull them closer in. Okay, kind of like those rubber bands, right? The more rubber bands you have versus electrons, the harder it's going to be to hold your fingers apart. Okay. Okay. Next, if I've got anions, so again, anions are your negative ions. Anions are larger than their neutral atom because when we add electrons, we're going to, one, increase how much those electrons are going to repulse each other. And so because they're going to be repulsing each other more, your protons, which again, you've got the same number of protons, is not going to be able to hold on to them as tightly. Okay? So it's kind of like if I had two fingers with two rubber bands on them. If I added a third finger to help those other fingers, they're going to be able to spread out that rubber band a little bit better. Okay. Okay. So here's the question. Which of the following has the smaller atomic radii? So I've got sulfur or sulfur with a -2 charge. So the sulfur ion. Okay. Well, here, sulfur has 16 protons and 16 electrons. Okay. Sulfur with a -2 charge has 16 protons and 18 electrons. Okay, so my question is, which is going to have the smaller radii? All right, well, let's talk about that repulsion. So here I've got more electrons repulsing. So since there's more electrons repulsing, they're going to spread a little bit further out. Okay, so since they're spreading out, that would make this one larger. Well, my question is, which is smaller? Sulfur then would be the smaller one. Okay? Which of the following would have a larger atomic radii? Okay, now this is, again, we're talking about those ions. So I've got strontium. Strontium is number 38 on the periodic table. So it's got 38 protons and 38 electrons. Strontium with a +2 charge has 38 protons and 36 electrons. Now, when it lost those 2 electrons, it dropped to the previous energy level. Okay, so now the electrons are going to be very similar to krypton. Okay, so we dropped an energy level. Well, if we lose an energy level, that means that our atom would have to be smaller, right? Okay, so then which one is larger? Would obviously be the one that has more energy levels. Okay. Now, here's a little bit more tricky one. It says, place the following in order of increasing radius. So I've got the oxygen. Oxygen has 8 protons. So we're just going to write 8 protons over here because there's so many of them, right? And then the neutral one would have 8 electrons. Then the one with the -1 charge would have 9 electrons. Positive one would have 7. -2 would have 10. And +2 would have 6. Okay, so now I'm going to be, again, comparing my protons to electrons. We're arranging them in increasing, right? So from smallest to largest. Well, the smallest one would be the one with the most amount of protons compared to electrons. Okay, we know that oxygen has 8 protons. So which one has the fewest number of electrons because would be the smallest. Okay, so oxygen with a positive 2 is going to be the smallest. So we have O with a plus 2, and then O with a plus 1, and then we would go to our neutral atom, and then we would have O with a minus 1, and then O with a minus 2 in terms of increasing our radius. Okay? All right. So that is talking about the size. And y'all, a lot of times the justification with size will also apply to the justifications with the other trends as well. Okay? So ionization energy. Okay, so ionization energy, its definition is going to be the energy required to remove an electron. Okay, so I'm trying to remove an electron. All right, so let's look at this. So in general, here's our justification, ionization energy decreases down the column because when we add another energy level or we increase the distance from the nucleus, we're going to reduce how much energy it is to take it away. Okay, so it's going to be easier to take an electron away the further it is away from the nucleus. Okay. Next, if we talk about across a period, as we move across a period on the periodic table, we're going to be having a larger number of protons, which again is going to increase that ZEF, or effective nuclear charge, which is basically that attraction from the protons to the electrons. And since I'm increasing that attraction, our size is going to get smaller, and thus it's going to require more energy to take those electrons away. Okay? All right. Now, here are some exceptions to the ionization trend within a period or row that can occur in two locations. Okay, so there's two places that you can see some kind of exception. All right. First, if we're talking about the transition from the s orbital to the p orbital, okay, so from s to p, that's going to happen because the p orbitals come towards the nucleus, and therefore it's going to require less energy to remove a p electron. Okay, so we'll talk a little bit more about that when we get to this part right here. Next, the transition from p3 to p4 can be explained because the increased repulsion created by the pairing of electrons within an orbital lowers the amount of energy required to remove that electron. So basically, because I'm adding an additional electron, they're going to be repulsing each other more because they're getting closer together. And since they're repulsing, it's easier to take one of those away. Okay? All right. So here is kind of the generalization of what we just talked about. So as a substance becomes more stable, removing their electrons takes more energy. Okay? So because of that, here is the list of stability from more stable to less stable. Okay, so let's talk about this. So if I remove an electron from a full energy level, that's going to take an extremely large amount of energy. Okay, so what I'm talking about is if I've got my full valence shell, so it's got 8 valence electrons sitting inside of it. Okay, if it is full, taking that one electron away makes it extremely unstable. And so because it's making it very, very unstable, it's going to take a huge amount of energy to make that happen. Okay, so we're talking about like if I've got something sitting at the quote unquote noble gas location for our electron configuration. Okay, so 1s2, 2s2, 2p6 if you're talking about electron configuration. So right here, I've got a full valence shell, because remember you can have 8 valence electrons. So my highest energy level can hold up to 8. So I've got 8. And so because of that, it's going to take a huge amount of energy to remove that electron away. Okay. Next, if I've got a energy from a full sublevel. So the sublevels, remember, if you remember from previous chemistries, you've got S, P, D, and F. Okay. So if I'm removing an electron from those energy levels, if they're full, it takes a larger amount of energy. Why? Because then you're going to have different amounts of repulsion that's occurring. Okay. So If I take it away, then we've got an off balance. Things don't line up or match up perfectly. And so since they don't match up anymore, we're going to throw off everything and make it much less stable. Okay. So that's what that means there. And then last, if we're moving it from a half full energy level. Okay, so if y'all remember when you did electron configuration, we talked about orbitals. Okay, so I have S. Remember, S could only hold 2 electrons. You would have one spinning up and one spinning down. If I had P, it could hold up to 3 orbitals, and each of those could hold 2 electrons. Again, one spinning up and one spinning down. So looking at this, that would be a full sublevel. If I looked at S and P, that's a full energy level. So then what would a half full sublevel or sublevel look like? So if I have S, one up and one down, and then I had P, and P was just up, 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 right? Because you always fill them in single before you double them up. So if I have here, this would be a half full or sublevel. So since this is half full, if I take this one away, we're going to be making that much less balanced. And so since it's less balanced, it's going to take more energy to remove that electron. Because remember, atoms are always about trying to achieve the most stable configuration they can. Okay? And then everything else is going to be less in terms of stability. Okay? So like if I had, for instance, this, let's get rid of that right there. This would be less stable than this would, because this is a half full sublevel. Okay. All right. Now, if we talk about ionization energies, so this is again the energy required to remove an electron. Okay. Well, we talk about them as removing electrons one at a time. Okay. So ionization energy 1 would be removing 1 electron. And then if we wanted to take another one, we would call that ionization energy 2 or IE2. Okay. If we moved to third, it would be IE3, and then fourth would be IE4. Well, as you remove more and more and more electrons, the amount of energy required is going to increase. Why? Because again, you've got the protons to the electrons, that ratio is getting off. You've got more protons now, which is going to be pulling harder on those electrons that are left over. So each time you remove one, it's going to take much more energy to remove. Okay? So again, as you continue to remove electrons, it will require more and more and more energy because your electron to proton ratio is decreasing. This means the remaining electrons are going to be held more tightly, and therefore it's going to take more energy to remove. Okay, so which has the highest first ionization energy? I've got sodium or magnesium. Okay, so sodium or magnesium. Well, sodium, if you all remember, sodium has 1 electron in the S sublevel. Sorry, I wrote 2. 1 electron in the S sublevel. Magnesium has 2 electrons in the S sublevel. So this would be a full sublevel, and this would be a half full sublevel. Okay, well, again, the more stable something is, the more energy it's going to take to remove an electron, right? Well, looking back at our stability chart, if we remove it from a full energy level, that's going to be the most stable, right? So it's going to take the most amount of energy. If we remove it from a full sublevel, that's going to be less stable than a full energy level, but more than a half full. So it's going to take more energy than half, but less energy than the full. And then if we've got a half full sublevel, it's going to take less energy than a full sublevel, but then it's going to take more than everything else. So this is half full, so it takes less energy. The magnesium is a full sublevel, so it's going to take more energy. So it's going to have, magnesium is going to have a higher first ionization energy, which has the lower first ionization energy. Okay, I've got calcium. So calcium has, again, because it's in group 2 on the periodic table, family 2, column 2, it's going to have 2 electrons in that s sublevel. And then strontium, well, strontium is also in there. So it's going to have 2 electrons. So then how do I compare them? Well, now let's think about what else we know. Well, since they've got the same number of electrons, we can't use our stability to help us in terms of zones of stability right here. So since it's got the same amount of electrons there in those sublevels, the next thing we have to look at is the distance from the nucleus. Because again, as I move further away from the nucleus, my effective nuclear charge, that pull from the nucleus, is going to decrease. Okay, so since I'm further away with strontium, it's going to take less energy to remove that electron. Okay, so strontium is further away from the nucleus, and as a result, it takes less energy to take that away. Okay, so for electron affinity, basically what we're going to be looking at is it's the opposite of ionization energy. So what it means is instead of the energy required to remove an electron, it's the energy required to add an electron. Okay, and it does follow the same trend as ionization energy for the exact same reasons. Now, the major difference is that electron affinity is going to be releasing energy. Okay, so electron affinity is a release of energy, and so if we're talking about the energy in electron affinity, we're going to be talking about it with a negative charge or negative sign. Okay, that negative charge. Okay, so if increasing electron affinity means the magnitude or the absolute value of that energy release is larger, and yet we're still going to add that negative sign. Okay, so anytime you talk about electron affinity, you should be talking about it with a negative charge with energy. But again, it's the same trend as ionization energy. So you can use that same justification when you're talking about it. Okay, so talking about stability, if I'm making it more stable, it's going to be requiring a little bit less energy than it normally would. Okay, so as I get further away from the nucleus, adding another principal energy level is going to require less energy in general. Okay, so we're going to follow those same general trends as ionization energy with electron affinity. Okay, and what I have found with the AP test is that very, very rarely do they talk about electron affinity, and they tend to focus on ionization energy or atomic radii. So yeah, keep that in mind. The last trend we have here is electronegativity. So electronegativity is going to follow, again, the same trend as ionization energy and electron affinity for the same reasons. Okay, so ionization energy and electron affinity, they follow the same trend. So increase in energy level makes it take less energy. Increase in Zeph makes it take more energy, that kind of thing. And electronegativity, its definition is the tendency to attract an electron. Well, you know, the same general trend applies, right? So as we get closer to something that is more stable, the tendency to attract it is typically going to be much higher, right? As we get further down the periodic table, because there's less attraction from the nucleus, it's going to be harder and harder to attract those electrons. Okay. So electronegativity is going to follow the same trend. Okay. The main difference between electron affinity and electronegativity is that electron affinity is an isolated atom's attraction for an electron. And then electronegativity is the atom's attraction for electrons it shares in a covalent bond. So typically when we're talking about electronegativity, we're going to be talking about how to make it share those electrons in a covalent bond. Okay. Now, here's something to note with electronegativity is you never write about electronegativity in terms of IMFs, okay? So we'll talk about IMFs later on, but when we get to it, make sure you never write about electronegativity with that, okay? It is an atomic bonding property, okay? So it's the bonding property in that atom, not between different molecules, okay? All right, so hopefully y'all understand our periodic trends. There is some practice that I've posted on Canvas. Please make sure to go in and work through those and let us know if you got any questions. All right. Bye.